All right, class, we're going to get started. So just before we begin, so today we have, we're going to finish up just a few smaller items on the lecture 7 notes. And then we're into lecture 8 on confidence intervals. We're going to be using the t-distribution and the normal distribution to compute confidence intervals about data. But before we begin that, just one note about the upcoming quiz. So we have quiz 3 on Wednesday in this room. So remember, one of the things we covered were different distributions, right? So we've now seen 5 different distributions in this class. Exponential, normal, and t-distribution are continuous, and then binomial and Poisson for discrete distributions. Most of those have forms that you can calculate relatively easily, the PDF and the CDF on a hand calculator, or at least you can calculate it on a hand calculator. But for the normal distribution, and as we'll see, the t-distribution, the CDF, which is what we use when we're trying to find the probability of finding an item within a certain interval. The CDF is in terms of an integral of this exponential function, which may or may not be possible to do on your particular hand calculator. So the solution to this is to go back in history, I guess, to how things would have been done before we all had Python, and to look at tables to compute these. So I'm not going to give you the full complex tables, because just learning how to look things up in these tables is an exercise in and of itself, and not one that I expect that you're going to have to do. But I will give you a simplified version of those tables of normal distribution and t-distribution to use on the exam. So this is an example. I think I'm going to cut down the number of entries on this as well, but this is showing you the normal distribution CDF as a function of z-score. Okay, so we have z-score, these columns down here, and then the CDF of z is shown here. Okay, so that way, if your calculator doesn't allow you to define an integral and compute that integral, or it doesn't have the normal distribution CDF already programmed onto it, this will allow you to look that up. Okay. And so I'll be providing this with the equation sheet on the exam. Does that make sense? Okay. So any place where you're going to take CDF of z instead of, for example, computing the integral of the exponential function that we defined as a CDF of z, you'll be able to look it up. And I'm not going to require you to interpolate on this table either. Okay, so it'll be just take the closest value, use the closest value. Okay. Again, to save you time and frustration, and because it's not a skill that I expect that you're really going to need. Okay. All right. Any questions on this or anything else before we get started? Yeah, go ahead. So the other distributions are defined in terms of things that you can plug into your calculator, and I would expect you to be able to plug them in. I'll give you the distribution definitions as part of the equation sheet, which I owe you, and we'll be sending out to you before the exam. Yeah, just for the ones that are in terms of an integral, those will have a table for. Okay. Other questions? Okay. So for example, you've already seen this on the first quiz, we had talked quite a bit about the binomial distribution, right? And so you calculated the binomial distribution probabilities on the quiz, right, from the definition, which was given on the equation sheet. So that's the kind of thing that I would still expect. Okay, any other questions? Okay. All right, so we had gotten almost all the way through lecture 7. I just want to show, which was on sampling. So this is an example that we're actually going to return to in lecture 8, so we won't spend too much time on it, just finishing up these notes. It's a question about, that actually came from lecture 2. Imagine that we have measurements of some pollutant that has some restriction on how much can be emitted. Those measurements are 72.7, 73.9, 74.2, and we want to know how confident we are that the emission limit is being met. And so when we talk about confidence intervals in lecture 8, the next set of notes, we'll be able to actually start to answer these questions. But for now, we can look at the mean standard deviation and now the standard error of that mean, which we'll be using later. So the mean 73.6, standard deviation is 0.794, and the standard error is about 0.5 kilogram per hour. So, and remember again, when we were discussing the standard error is tells us about the distribution that we would expect to see, the distribution of mean values that we'd expect to see from a set of 3 measurements in this case. So the standard deviation tells us about the distribution of individual measurements that we would be making from this plant. So we expect to see, about a 0.8 kilogram per hour standard deviation in terms of the range of individual measurements that we make from this plant. But if we're now taking 3 measurements and taking the average of those 3 measurements, we're going to see a smaller number, right? We're going to see a smaller distribution of the average of those 3 measurements. And this is telling us that we expect to see a standard deviation of about 0.5 from those. And again, we're going to get back to this in the lecture 8 notes. This will kind of set up a little bit of lecture 8 as well. So let's say we have so this is again about using the t-distribution. So now we're going to go a little bit further. We use the t-distribution to ask to see about a particular claim. We're saying this wastewater treatment plant claims that its effluent has mean suspended solids concentration always less than 40 milligrams per liter. And however, 14 samples measured on a particular day have a sample mean, right, that X bar of 46, and a sample standard deviation indicated as that lowercase s of 9.4 milligrams per liter. Let's say that we have previously looked at this and seen that the concentrations follow a normal distribution. So we expect to see the data normally distributed. So what we want to know is, do these data weaken or support the plant's claim that the mean is always less than 40 milligrams per liter? Right, so we had a mean greater than 40 milligrams per liter. Is that a reasonable claim? And so what we're going to do is we're going to use the t-distribution to figure out the probability of observing a mean of 46 or higher for this given sample. Sorry, what was going on back there? Let's see. Camera pointed up at the front of the room. Just curious what was going on. No, yeah, you too. Oh, yep, yeah, sorry. Yeah. Oh, was something else on the phone? Okay. Yeah, sorry, that's okay. So we're going to say that if the actual mean of this data is 40 milligrams per liter, our sample mean was 46 milligrams per liter, and we had a sample of 14, we're trying to see what is the probability that we had that this data could have come from a plant with an actual sample mean of less than 40 milligrams per liter. So even though we saw an actual average of greater than 46, there's a probability that that data was, that those were all outliers from this particular set of measurements, and that the actual plant mean emissions are less than 40 milligrams per liter. And so that's what we're going to be using the t-distribution for. And if we note to compute the t-distribution, we now have to know both the observed mean, right? The sample mean was 46. The actual mean of the population, which in this case we're going to say is 40. And we have our S over square root of n, again, is the standard deviation of the means that we expect to see. And remember that the t-distribution also has this additional parameter, which is degrees of freedom. It tells us basically how wide or narrow the distribution of values that we expect to see is. In this case, our degrees of freedom, the way we find that is as n minus 1. We call that the degrees of freedom of the t-distribution. In this case, the degrees of freedom is n minus 1 is 14 minus 1 is 13. So if we take that data, we can then compute our t statistic, which is, again, just as defined above, the mean minus the sample mean minus the what the plant manager told us was the actual maximum mean over the standard deviation of the sample means. And so what we get is a t statistic of 2.4 from comparing those values together. And so then we can find the probability of observing a mean value from 14 measurements of 46, given that the true mean is actually 40 milligrams per liter. By looking at the, by using the t distribution, in this case, we're going to find the CDF, right? The t distribution CDF for that value of the t statistic and for the specified degrees of freedom. This is a little bit distinct from, remember, the normal distribution. We just had the normal distribution CDF was just defined in terms of the z-score. But for the t distribution, remember, it's really not just one curve. It's a whole family of curves that vary as a function of degrees of freedom, right? So the if we look at our t distribution, we can see that it changes shape a little bit as we change the degrees of freedom, right? So the normal distribution is a single curve defined in terms of z-score. The t distribution is a range of curves that are defined by both value at a given t-score and the number of degrees of freedom. And so when we evaluate the CDF for our t statistic and this number of degrees of freedom, we see that we have a very low probability, 0.016, so less than 2%. And this is telling us that the probability that the true mean is 40 milligrams per liter is pretty low, given that we had this measurement at 46 milligrams per liter. So it's highly likely the mean is greater than 40 milligrams per liter. So what we're essentially trying to do here is use the, so if we could just step back up here for a second. We want to evaluate this claim that the mean value is less than 40 milligrams per liter. We made some set of measurements. So it's possible that our set of measurements were just happened to be on the high side of of the values of amount of effluent that is being produced by this particular wastewater treatment plant, right? We were just there, we had some particularly bad samples or something. I mean, from the outset, you might say it doesn't seem like it's likely, right? Kind of intuitively, it seems like it's not likely that the actual average of the suspended solids concentration is less than 40 milligrams per liter, right? Because we measured 46 milligrams per liter, right? So it seems like the value is probably greater, that the actual mean is probably greater than 40 milligrams per liter. But what we're doing here is we're using the t distribution in order to, put that to the test, like put an actual number on that. So based on the measurements that we made, we see an average greater than 40, right? We see an average of 46 with some standard deviation of 9.4 milligrams per liter. And the t distribution tells us the probability that we observed, right, made those measurements with an average of 46, but they actually come from a distribution that has an average of 40 milligrams per liter. Does that make sense? So it's possible, it's theoretically possible, in this case, we're saying that there's about a 2% chance that even though the actual true average of wastewater suspended solids concentration from this plant is 40 milligrams per liter, there's a 2% chance, or like a 1.6% chance, that on a given day we make 14 measurements and have an average of 46. So there's a chance that on a given day we just happen to get measurements that are greater than this mean. But what this is telling us is that that chance is pretty low. So there's only about a 1.6% chance that these measurements are possible. And so it allows us to just go a little bit further than saying it doesn't feel right. Right? We can actually put a number on how likely that actually is. And we'll talk quite a bit more about this, starting with the next lecture on confidence intervals, or the next material on confidence intervals. The last thing that's in here that is, I just want to go over before we get to the LO8, the lecture 8 notes, is about how we tell that a distribution is actually normal. So the, one way is by plotting the histogram, right? So we've looked at what a histogram of a normal distribution looks like. We have this kind of bell-shaped curve that's symmetric with two tails going out from either side. But for example, just gonna scroll up again, the t distribution nominally looks pretty similar to the normal distribution, right? So it's not necessarily, just from looking at the histogram and seeing kind of a bell-shaped curve that's symmetric, that doesn't on its own tell you that you have normally distributed data. So another useful way of looking at data to determine if it's normal is to plot what's called a normal probability plot. And this is, so a way to generate this in Python, we can use prob plot, will allow us to see this. And when we do this, we get the data now plotted as so all of the individual values within our data will be plotted in ordered values versus, I believe this should be the z-score on the x-axis. And what we see is that if we have normally distributed data on one of these probability plots, we should see all the data more or less lying along a straight line. And so really what this allows us to do is evaluate if the tails of the distribution are close to what we expect to see for our normal data. So for example, if we have an exponential distribution, which we talked about in lecture 6, then we see that there's strong deviation from the normal distribution, from the expected straight line for the normal distribution, indicating that we do not have normally distributed data. So the main thing I really want you to take away from this is that this probability plot, we can think of it as a tool to help detect normality in the data set. So as an example, we said that the data from this wastewater treatment plant were previously shown to be normal, or previously shown to be normally distributed. This would be one of the tools that we could use to show that the data is normally distributed. Okay. All right, any questions on the end of this lecture 7 notes to begin with? Okay, so again, remember in lecture 7, we talked about sampling. We introduced the t distribution as a tool for looking at the expected values for a sample mean. And remember, a lot of times in statistics, one of the parameters that we're really interested in is the average that we observed, right? We make a number of measurements and we want to ask questions about the average that we've observed. How likely is it to fall within a certain range, this kind of thing. And so we can use the t statistic and t distribution in order to do this, which is what we just introduced. So next is lecture 8, where we're going to talk about confidence intervals for the average value that we observe. So this is where we get into really more rigorously looking at what is the probability of seeing a mean of a specified value or within a specified range. So for example, that question that we first raised in lecture 2, that we just looked at again, we computed the standard deviation of the mean in lecture 7, where we had 3 values, 3 measured values of some pollution emission. And we're trying to ask, is that within federal standard? we'll be able to actually start to address that question using the material now in this lecture 8. So any questions before we move on? Okay. All right, so we learned that standard deviation of the mean is given by the standard deviation of the population divided by square root of n. So this is like if we make n measurements of from a given population, right? So we take a sample of n measurements from a given population. This tells us about what the distribution of mean values we would expect to see. Or let's say, put another way, let's say we have a population of all students at University of Utah campus, and we want to know about the range or about the heights that we would measure, the average height that we would measure from a sample of 10 students from the University of Utah campus. If I ran that experiment many, many times, if I sampled 10 students and then another 10 students and another 10 students and computed the mean of each one of those samples, then what I would expect to see is a distribution with a standard deviation of sigma, the population standard deviation, over square root of n, over square root of 10. So it tells me about the spread in computed mean values for my sample. So it also gives us this sense of diminishing returns, where if I increase the size of n by a factor of 4, I only get a factor of 2 decrease in the spread of, or in the range of mean values that I measure. So if I go from a sample of 10 to a sample of 40, I would only see, I would expect to see the standard deviation, or the spread, the range of mean values that I get back as is only going to decrease by a factor of 2. We saw that the expected value of the mean of my sample is equal to the mean of the population. And this number, the standard deviation, is sometimes called the sample standard error, or SE. So the standard error tells us something, right? So standard error is the standard deviation of the mean values that we would measure if we were to make our measurement, take our sample many, many times, right? Then this is the spread of values that we would expect to see. Remember, like if our population is the heights of students at the University of Utah, there is only one average value, right? There's just a single population average value. But now if I'm only going to ask 10 students what their heights are, I'm going to get some value which is different from that average value. And for every sample of 10 students that I ask, I'm going to get a different value. So there's some uncertainty in what the actual mean is. Even though I sample 10 students, there's some uncertainty in what the actual mean is. In some sense, I don't know the real mean of the overall population that well, right? Just from my sample of 10. And so we can think of the standard error as telling us something about the uncertainty in our average, right? So I sampled 10 students. There's some uncertainty in how well I know the true average, right? The true population average. And so, I can take more samples, right? I can increase n in order to decrease my uncertainty, decrease my standard error, and get a more certain value. So related to that uncertainty, we said that when we have large samples, so typically n of at least 30, then our distribution of values that we got from from samples that we get from our sample will be approximately normally distributed. And therefore, will be approximately normally distributed with the mean equal to the mean value and a standard deviation equal to the standard error, sigma over square root of n. And so that means that I can then use I can then find the probability that my sample mean lies between, let's say, two different values, is going to be the probability of having a z-score within the two corresponding values. So it'd be like a minus mu. So the probability of finding a sample mean between A and B would be the probability of having a z-score between the values that correspond to A and the z-score that corresponds to B. And so we can then, and that's what's rewritten down here in equation 5. So the probability, again, for n greater than 30, the probability of finding a sample mean between two values, A and B, is equal to the probability that I have a z-score for the normal distribution between those values of A and B. So for example, if we, in this case, we're going to find probability of getting a z-score such that the probability of finding our mean between A and B is 0.95. So if we want to find essentially the z-scores that are going to give me 95% confidence that our mean lies within that particular interval, we can define this down below. And we end up showing that for z-scores of plus or minus 1.96, then we end up with 95% of the area underneath our normal distribution lies between z-scores of negative 1.96 to positive 1.96. So and these numbers will come up quite a bit because oftentimes we use a probability of 95% as just a handy way of indicating that something is likely. So in statistics, what we'll see is that we don't have an absolute answer that something is definitely going to happen or definitely not going to happen. All right, so in the example from the previous lecture notes, we saw that even though we'd measured a mean of 46 milligrams per liter and the plant operator is telling us that their average is always below 40, there was only maybe 2%, there was about a 2% probability that the plant operator could be telling us the truth, right? And we still had that measurement with an average of 46 milligrams per liter. But oftentimes we have to set a cutoff someplace. No matter how good our numbers were, we're never going to get to identically 0. So we often use 95% as kind of a practical limit, where we say that if we can make a statement with a probability of at least 95%, we'll often say that's good enough. Now, what's good enough will depend on exactly what situation you're dealing with, but 95% is where we often start. And so if we put this back into our expression up above, we'll say that we have a 95%, so again, for n greater than about 30 or so, the probability of getting so for n greater than about 30 or so, if we know for example, the sample mean, or we're asking a question about what the sample mean is. Sorry, we have the sample mean. If we know what the population mean is, or we're asking a question about the population mean, then there's a 95% probability that the z-score associated with that sample mean is between minus 1.96 to 1.96. So we can rearrange this and use this to then compute confidence interval based on this 95% probability, where we're going to be finding, we're saying that there's a 95% probability that the mean, so if we have a given sample, there's a 95% probability that the true mean, right, the true population mean, lies between within about 1.96 times the standard error that we computed from that data set. again, for n greater than about 30. So again, thinking back to our experiment, let's say we're trying to measure or we want to know the average height of University of Utah students. Right? We took a sample. Let's say we take a sample of 40. So we're greater than that n is equal to 30 requirement. So we now poll 40 students. We ask for and we measure their height. We then compute the mean of that sample. That's our X bar. And we compute the standard error of that sample, right? The standard deviation that we measured divided by the square root of 40. What we would then say is that we expect with 95% confidence that the true mean, the population mean, is within this range of minus 1.96 or X bar minus 1.96 standard times the standard error to X bar plus 1.96 times the standard error. Right, so we expect that we have 95% confidence. We expect that the true mean is within that range. So one consequence of this, right, 95% seems like we're pretty confident, but that means that there's about a 5% chance that we're wrong, right? So there's a 5% chance that the true mean lies outside of that range of plus or minus 1.96 times the standard error. And that's 5% chance is about 1 in 20. So we expect about 1 time in 20 that we're actually wrong, that our true mean is outside of this range. And so this is data, or some sample data, where they're computing this range, X bar. We might sometimes write this confidence interval as plus or minus whatever the range is, right? So this is the mean plus or minus the range. And so imagine we run this experiment, we ask 40 University of Utah students their height, because we want to know the overall average of the actual population. And let's say in this case, we know that the overall average is some value here given by this dashed line. And now we're going to take each one of those samples of 40, plot the mean here as this dot, and plot the range using these range bars. What we find is that for any given value is not going to be exactly on, right? Any given measurement that we make is not going to lie exactly on this line, right? Because our sample mean is likely to be a little bit different from our overall population mean. And if we do this many, many times, at some point, right, with probably about 1 in 20 or so, if we did this many, many times, we would end up with a sample mean that is far enough away from the true population mean that this 95% confidence interval does not overlap with the true population mean. Okay. So that's when we're looking at, in this case, this confidence interval is telling us that we have only 95% confidence that the true mean is within this range, which implies kind of the inverse, that about 5% of the time we're going to be wrong. Okay. Yeah, go ahead. Yeah, so let's say the example of University of Utah student height, right? And we don't. So in this case, so we're computing it. So we would compute the confidence interval. So in general, we don't know the true population, right? So generally speaking, we just have our measurements, and we're using those measurements to try to say something about the true population, right? So so most of the time we don't know where this dashed line is, right? All we can do is take our sample, right? Let's say 40 individual measurements of height, and ask, and use that to infer something about what this dashed line is. Does that make sense? So we have to then compute this confidence interval based entirely on the data within our sample, because we don't know what the actual population mean is. Yeah, so in this example, so if we're trying to translate this into an example, let's say that each dot, this would be like the mean of one sample of 40 students. And this would be the 1.96 times the standard error that I computed from that individual sample, right? This would be another sample that I made. This would be another sample that I took. And then what I'm saying is if we knew what the true mean was, and we plot that as the dashed line down the middle here, then we would see that about 1 time in 20, this range would not overlap with the true mean. Does that make more sense? Yeah, so each data set would be 1.96 times the standard error computed from that data set. Does that make sense? Okay. Because again, typically we don't know the true population mean or even the true population standard deviation. Right? Typically all we know is what we measured. And so we're still going to use that to make statements about our, in this case, the population mean. But it's probabilistic. It's inherently probabilistic. There is some chance that we're wrong. And we're expressing that as in this, when we say 95% probability, that implies there's a 5% chance that we're actually wrong. No, that's okay. So 1.96. So when we have n of greater than 30, greater than about 30, then we know that the distribution of mean values for a process that itself is normally distributed, which describes a lot of processes, will be normally distributed, right? Because the t distribution becomes a normal distribution when n is greater than 30. And so that's where that 1.96 came from. Okay, does that make more sense? Okay, other questions? Yeah. So the 1.96 for normally distributed base data and a 95% confidence interval with n of greater than 30. Yes. Yeah. So universal with very big caveats. Yeah, but yes. Yeah, so the standard error was based on the standard deviation of our sample. And so there's error in the standard error as well. And that's but that is included in this estimate of 95% confidence. Yeah. Other questions? Okay. So in general, we can write this confidence interval using the normal distribution, right, for something other than 95% confidence interval as x bar plus or minus z, and here it's written as alpha over 2, where alpha is the confidence level, times the standard error, again, from our sample. So alpha is what we refer to as our confidence level. It's written here as alpha over 2, because if we look down, let's look at this example here where we have a 98% confidence interval. So alpha is now 2%. We're going to find the z-scores that correspond to 1% and 99%, which are going to be z-values of minus 2.32 to 2.32. What that really means is, if we look at our normal distribution, we have 90, or remember our alpha, our significance level was 2%. So what we're trying to find is the range around our mean, under which we have 98% of the possible values. And so that means to get to this 98% of the possible values, we go out to our alpha over 2, right, 0.01, and the other way, there's 1%, or alpha over 2 fraction of the area is outside on either side. That makes sense? So the total area under our curve is 1 minus alpha, where alpha is our significance level. And because this is symmetric, that implies that we have alpha over 2 is the area under the curve on either side of this range. Make sense? So we have, so if alpha were 5 or 0.05, we would have 95% of the area. We're looking for the z-scores, in which we have 95% of the area under this curve, meaning there's 2.5% on either side as we go out, right? And we knew that that occurred at a z-score of 1.96, or plus or minus 1.96. So yeah, it's alpha, significance level or confidence level. So if we say the confidence interval is 95%, we say significance level is 5%. And this quantity z, the z-score times that standard error is called the margin of error, and it's been abbreviated here as MOE, often in the notes. So we'd often write our data as the mean, right? So the we would say that for data where the mean values satisfies the normal distribution, so for n greater than 30, then our confidence interval on the, we often express our confidence interval on the true population mean as the sample mean plus or minus the z-score times the standard error. So we'll go back to this example, right, where we have a plant with where we made some measurements, 72.7, 73.9, 74.2 kilogram per hour as the emission rate of some pollutant. And we want to know how confident are we that the pollution rate is actually underneath the limit, right, whatever the statutory limit is of 75 kilograms per hour. And the first thing we're going to do is we're going to say, so we know that we can only use the normal distribution to look at the range of mean values if n is greater than 30. In this case, we only have 3, right? We only have 3 measurements. So we're going to start with trying to use this, like incorrectly use the normally distributed data, normally distributed model anyway, and see what answer we get. And then we're going to compare it to the answer we get when we do it the right way. Okay. So in this case, yeah, so the sample size is not large, and so we can't use the normal distribution. So it's far too small, right? We're going to get an answer that is definitely incorrect if we use the normal distribution. But nonetheless, we're gonna plunge ahead and see what happens. So we're going to plug in. So in this case, we have our sample data put into this vector here, and there is our significance level of 0.05. This function here defines or will return the statistics or some simple statistics on our data, including the mean, standard deviation, standard error. In this case, we're going to use the normal distribution to find the confidence interval at our significance level of alpha. And we'll then compute the margin of error on our data using, again, this normal distribution. And again, just note here, we have DDOF, the delta degrees of freedom for standard deviation is equal to 1. So again, we're using NumPy, and NumPy assumes that DDOF is equal to 0, but we have a sample here. So we need DDOF equal to 1. So if we run this function for our list of data, and we had alpha is equal to 0.05, so we're going to be making the 95% confidence interval, we end up with a 95% confidence interval for the mean of 72.7 to 74.5 kilograms per hour. So again, based on the incorrect assumption that the data is normal, that the mean values that we would see here are normally distributed, we end up with this range of values. And we'll compare that to the correct calculation just down below. We can also, there's a built-in function that can calculate confidence interval using z statistic as well. this case, it's just this norm dot interval function. We'll do the same thing. Okay, so you can define your own function as was defined above, or we can use this norm dot interval as well, and we get the same result. But all of this kind of begs the question of what happens, like what should we do, right? So what should we do when we have data with n of less than 30, right? So if we don't have that large of a sample size, in this case, we're measuring pollutant emission, which maybe was a very expensive thing to do. So we only have 3 data points. We know that we can't use the normal distribution to estimate a confidence interval on our mean value. So what should we do? And the answer is to use the t-distribution, right, which we discussed in the last lecture. So remember, the t-distribution is what shows us the range of sample means that we expect to see when n is small. Right, when n is large, we expect to see something normally distributed, but when it's small, we use the t-distribution, where now instead of the z statistic, we have this t statistic. It's defined the same way. It's just x bar minus mu over the standard error. But the shape of the t-distribution is a little bit different. It's a little bit wider than the normal distribution. And that shape of the t-distribution is described by the degrees of freedom. It's the only parameter that determines the shape of that t-distribution. And we find the degrees of freedom as n minus 1, where n is the sample size. Okay. So in terms of now this t statistic, which is what we're going to use again if n is less than 30, then we can again write confidence interval on our sample mean. So for a given a confidence interval on our population mean for a given sample mean, standard deviation, and number of samples. Very similar to what we had for n greater than 30. But the main difference here is that now I have this t statistic that I'm using instead of the z value. Right, so that's my primary difference here. And so here in this code, we're now actually going to compute the confidence interval at 95%, at 5% significance level, using the t statistic. And now note here, we're using this function to find this PPF function. We'll find the t statistic that corresponds to a given level, a given value of alpha. In this case, this is in terms of the area under the curve, right, that we have. And now we also have to have the degrees of freedom. Right, and that degrees of freedom determines the shape of our t-distribution. In this case, given by n minus 1. So in this case, our degrees of freedom, 3 measurements minus 1 is 2. Right, so we have 2 degrees of freedom in this measurement. And then this code will then use that to compute the margin of error and confidence interval on the data and display that data down here. And what we see is that we end up with a margin of error in this case of 1.97 as compared to, and I'm just going to scroll up for a second, the margin of error that we saw when we incorrectly applied the t-distribution was 0.9. So what that's telling us is that when we made this incorrect assumption that we applied the normal distribution to try to measure the range of mean values that we might expect from our experimentally measured set of 3, we got a smaller margin of error. So it gave us an overconfident estimate of what the true mean of the population really was. So the t-distribution, remember, is wider than the normal distribution. So it has, we would say it has heavier tails, it has bigger tails than the normal distribution. So there are more outliers. The t-distribution accounts for the fact that we expect, when we have a small sample, we expect to see more outliers than when we have a really large sample. And so the t-distribution tells us that, that really we expect to see the true population mean within about 2 kilograms per hour of what our measured sample mean was. And what that translates to is a 95% confidence interval on the mean of, or a 95% confidence interval on the mean is that it lies somewhere between 71.6 and 75.6 kilograms per hour. And if you remember back to this example, the federal or the limit, whatever it was 75 kilograms per hour. And so there's a chance to a significant level of 0.05 that the true mean is above 75. Okay, so when we, but if we had used the normal distribution, we would have gotten that wrong. So again, just like with the normal distribution, we don't have to write our own function to compute the t, or to compute confidence intervals using the t distribution. There is a built-in function. So in this case, we're using this t dot interval function, which again takes our significance level, as well as the number of degrees of freedom. And we're also then giving it the mean and the standard deviation as the center, the location of the mean, as well as the scale of that distribution. And this then returns the 95% confidence interval, in this case, 71.6, 75.6. It's the same as what we computed using our own function above. So we can see that our 95% confidence interval, right, from those three measurements, even though those three measurements had a mean that was below the limit, we cannot say with 95% confidence that the mean is not greater than the limit, which was 75. But what we haven't done here then is answer the question of what is the probability that the limit is greater than 75 kilograms per hour. So we can invert this and ask ourselves, right, so the 95% confidence interval does include that emission limit, even though the sample mean was 73.6. So what we can do is use the same, the t distribution to answer this question of what is the probability that the true mean is 75, but the, right, so the true mean, the regulatory limit was 75, but we saw a range of values given by that vector there. So this is computed here. So we're using the more or less the same range of calculations here, but now we've added in this estimate of the t statistic. So this t limit is telling us the t statistic based on the observed sample mean, the observed sample standard error, and that limit number, right? So that 75 grams per hour number. And then we're going to find the probability as 1 minus the cumulative density function for that t statistic. And again, we're defining the degrees of freedom because we have a t statistic curve, and we know we have to define the shape in terms of the degrees of freedom. So to think of it another way, the CDF of that t distribution is going to give us the area under the t distribution all the way up to whatever the specified value of our t statistic is. And so then the probability that we're out in the tail, that's out all the way on the far side, is going to be 1 minus that probability. That's why we're doing that 1 minus t dot CDF. And now when we do this, we find that so first of all, the t statistic value for that 75 kilogram per hour was 3. And our probability that the emission rate exceeds that limit, in this case, we're putting as a 0.046. So our end result of this analysis was that we're 95% confidence that the mean falls within this interval. But we concluded that there is a probability, about 4.6%, that the actual emission rate exceeds the 75 kilograms per hour. So, so there is a chance that actual emission rate exceeds that number, but it's not terribly high based on our sample. So in summary, so overall, what we've shown is that for a population mean, we can write the 1 minus alpha times 100%, or the 1 minus significance level percentage confidence interval is given by the mean of the sample plus or minus the t statistic for that significance level over 2 times the standard error. Or again, our standard error was our sample standard deviation over the square root of n. Yeah. Because, well, generally, yeah, so the question is, if the t-distribution approaches a normal distribution for sample greater than 30, why not just use the t-distribution for everything? And you can, and you'll get the right answer. What you'll see is in tables of, for example, the t-distribution, or if you were to compute the t-distribution as your number of degrees of freedom, let's say you compute t-distribution for a 95% confidence interval, right? The value of the t statistic for 95% confidence interval, and you vary n, right? You just keep increasing n. And what you'll see is that it approaches 1.96. And when you get to about 30, it becomes about 1.96. And from there, it doesn't change. It's just, yeah, so you can do it that way, and that's totally fine. Yeah.
And then as well with the
yeah. Yeah, so the question is, would the normal distribution work if we have normally distributed data that's not like means, like weights? Then yes, that's exactly. We use the normal distribution then to find the probability of getting. So let's say we have a population with a given mean and standard deviation. And let's say it corresponds to heights of students at University of Utah or something. And we want to then know the probability of finding an individual height that is a certain z-score away from the mean, right? Then we use the normal distribution in order to find that. This is just saying that, and there in that case, the standard deviation we use is the standard deviation of the population, not the standard error, right? Because we're making a single measurement and we're saying it's normally distributed. I guess another way, the reason we start with the normal distribution is we said that for n greater than 30, the mean for a sample size of n greater than 30, the means are normally distributed. And therefore, we can use the normal distribution to describe it in the same way that we could use the normal distribution to describe like the height of University of Utah students, individual measurements of University of Utah students. Does that make sense? Okay. It's just that then so we can almost think of n less than 30 as like a special case where we then have to use this other distribution. Yeah. But I could have done it the other way too, where we start with t and then we end up with normal. Okay. Other questions? Okay. So I'm just going to go over the last 2 items on this. The last one is one that we've seen before, but I just want to, now that we've talked about confidence intervals, just review that concept again. We can also do this. We can also apply the same kind of estimate to look at the proportion of a population that, let's say we have something that is binomial, that's true or false. We can then find the proportion that we have a population within a certain range, or a fraction of the population within a certain range, as again using a very similar kind of statistic, assuming that in this case that statistic is normally distributed for which is generally justifiable for NP greater than 10, and this n times 1 minus p of greater than 10. So basically for a fairly large population, where we're looking at the proportion that we see a specific event occurring. This is telling us that we can use, basically, we can assume that the proportion of a particular event happening is roughly normally distributed. Again, assuming that we meet these conditions, that the number of events that we see that are positive is greater than 10, and the number of events that we see that are the negative are also greater than 10. But the modification here is that the standard error, again, based on more or less our binomial distribution, is the square root of p times 1 minus p over n. So we can use the same kind of reasoning and do the same kind of confidence interval calculation using normal distribution with this estimate of what the standard error is for the population proportion. The last piece here is about linear regression. And so here's an example that I encourage you to look through that's in the notes on linear regression. But what we end up with is we're actually going to use if you remember back to our linear regression lecture, we talked about confidence intervals on the parameters of the linear regression. And so in this case, we're actually then using that in order to make an estimate of from experimental data using that linear regression data. In this case, we're plugging that into our linear regression values. Right, and we have that down here, confidence interval for slope and intercept. And again, these are the expressions that we had from previous lecture. All right, with that, it's going to end our lecture on confidence intervals, lecture 8. Any questions on this? Yeah. Yeah, so lecture 8 will not be on the quiz. Lecture 7 will be on the quiz. And so the material we covered today from lecture 7 was an example of application of what we had covered on Monday in lecture 7, and something that requires a Python library to compute, right, where we looked at those normality curves. So the normality curves are not going to be on the quiz, but the thing that we did an example about, that's something that could be on the quiz potentially, but lecture 8 will not. Yeah, sorry, last Wednesday, not Monday. Yep.
Like the first